Okay, I'm going to be continuing here the 8.2 homework. I'm going to be doing 25 through 28, then I'm going to be doing like 31 through 30, maybe 34. So 25. Sum n equals 2 to infinity of 2 over n squared minus 1. All right, so we take a look at this. It's not geometric because I don't have a number to the power n. If I try my nth term test on this, okay, so let me try the nth term. Limit n goes to infinity of 2 over n squared minus 1. This goes to 0, so this test fails. And so I've got to figure out something else. All right, well, let me try something else here. I could possibly look at maybe it's harmonic, so it diverges, but see the denominator is not linear. So we have a constant on top, but we have a quadratic on the bottom, so that it's not harmonic, so we can't just conclude it diverges. So maybe we can factor out that denominator. How about that? And that'll give me n plus 1 times n minus 1. Now, I cannot split this up into two different series, you know, one like with 2 over this and 2 over that, because you can't work with fractions that way. Each one of these by themselves are linear, but multiplied together is quadratic. So we're still not going to get harmonic that way. But what we do is we go back and we realize, oh, wait a minute, we could do a partial fraction decomposition on that. I can try and rewrite 2 over n plus 1 times n minus 1 as, I have two distinct linear factors, so a over n plus 1 over b over n minus 1. And then going through, so we did this when we were doing integration with partial fractions. We go ahead and try and determine what a and b are. And let's see, if n is 1, then it kills off this, and we get 2 equals b times 1 plus 1 is 2, so 2b, so b is 1. So know what b is. If n is negative 1, it kills off this one, and I get 2 is equal to negative 2a, so a is negative 1. Negative 1. All right, so that means I can rewrite this series as series n equals 2 to infinity of, let's see, negative 1 over n plus 1, and then over here plus 1 over n minus 1, like that. You know, I'll just leave it like this. Okay, so at this point you might think, okay, well, sure, this is going to diverge because this is harmonic and that diverges, and this is harmonic and that diverges. However, this one diverges, but it's negative. So it's going to like negative infinity. This one's going to positive infinity. So what you're getting is something like negative infinity plus infinity when you break this up into two sums, and that we've never been able to determine. Now, if one of them goes to negative infinity and the other one goes to a number, of course that's going to diverge, or the other way around. If this went to a number and this went to infinity, that would diverge. But the fact that they're both going to infinity and one of them is negative and one of them is positive, we cannot figure out what that is. So we've got more work to do here. I just got a text, so let me just check what this is. Okay. All right, so let me try and write out the first few terms of the sequence. And you know what I'll do, since this is my first one, I'm going to write out the first few terms using this first. If I let n be 2, I get 2 over, see, 2 squared is 4 minus 1 is 3. If I let n be 3, I get 2 over, let's see, 3 squared is 9 minus 1 is 8. And then the next one, 2 over, let's see, n is 4 now, so 4 squared, 16 minus 1 is 15. And then 2 over, let's see, n is 2, 3, 4, 5, 25 minus 24. And so, I mean, oh, sorry. doing the sequence. I took a break and I've lost my train of thought here. So this is what we've got there. I don't really see anything happening that is going to help me figure out what's going on. But if I rewrite it this way, watch what happens. So if I let n be 2, I get, and I think what I'll do is I'll write this over here. If I let n be 2, I get -1 over, let's see, 2 plus 1 is 3, plus, let's see, I'm at n be 2, so 1 over 2 minus 1 is 1. Plus, now I let n be 3, so I get -1 over 3 plus 1 is 4, plus 1 over, let's see, 3 minus 1 is 2. And then plus the next one, -1 over 5. And then I get plus 1/3. And then plus -1 over 6 plus 1/4. And that's what keeps happening. So I look at this and I notice something. I notice that this -1/3 would actually cancel out with that positive 1/3. Those two would actually go away. And then the -1/4 would cancel out with this positive 1/4. And the -1/5 would probably cancel out with the 1/5 I would get down there. And the -1/6 would cancel with something I would get down there. So I'm noticing this is going to be a collapsing series. Now, they tell you that inside, in the instructions, they tell you it's a telescopic series, which is also called a collapsing series. They give you that information, but you should be able to notice it yourself. So look at this series, say, it factors, and do your partial fractions. So the proper technique, once we understand that it's a collapsing series, the proper technique is to do the following. You first find S sub n, which is the nth partial sum. Once you find out what that is, then you let n go to infinity. Or in other words, you find the limit as n goes to infinity of that nth partial sum. So we got kind of two steps here, all right? So let's do the first step. Let's find S sub n. I'm going to need some space for this, so I'm going to write it out like this. S sub n is the sum that I get here when I start at 2, right, and I stop at some n here, capital N, let's say, and that's what this is, like a capital N. Okay, so I'm going to start at n equals 2 and stop at some capital N. So what do we get when we do this? Well, we already did the first one. It was -1 over 3 plus 1, and then it was -1 over 4 plus 1/2, and then it was, I forgot the plus sign between those. -1 over 4 plus 1/2, and then it was -1 over 5 plus 1/3, and then -1 over 6 plus 1/4, and plus ... And now what we'll do is we'll write out the last ones, and I'm going to start over here. The last one would be what I get when I plug in capital N, which is 1 over capital N plus 1 plus 1 over capital N minus 1. So that's what happens when I plug in N. The one before it is what I get when I plug in N minus 1. So plug N minus 1 into this, you get -1 over N minus 1 plus 1 is just N, plus over here 1 over N minus 1 minus 1 is N minus 2. And we'll look at the one in front of that. This is what I get when I plug in N minus 2. So if I plug in N minus 2 here, I get -1 over N minus 2 plus 1 is N minus 1. Plus, if I plug in N minus 2 here, I get 1 over N minus 3. And I'm hoping that's enough for me to establish the pattern of what's going on here. So notice that the first number in the first parenthesis is going to be killed off by the second number 2 parentheses away. So let's see, the first number in a parentheses should be killed off by the second number 2 parentheses away. Yes. The first number should be killed off by the second number in the parenthesis 2 away. So it would be 1, 2, it would be in here somewhere, and that negative 1/5 would go away. This 1/6, negative 1/6, would get killed off by something in here. It would go away. Now, on the other hand, you could look at it backwards. The second number in a parentheses gets killed off by the first number 2 in front of it. So the second number in a parentheses gets killed off by the first number 2 in front of it, and so on and so forth. So look at this second number. For it to get killed off, we need to have something in a parentheses 2 in front, which we don't have. So this number stays. Nothing touches that one. This is the second number. I need to be able to go 2 in front, which, again, I can't. So that stays. This second number, yes, it did get killed off by that one. And now I come over here, I do the same thing. The first number should get killed off by something second number 2 away, which is here. Right? This first number, I cannot go out because I stop here at n. So there's nothing that kills that, it stays. This first number, I need to go this way. I can't go anymore, so this stays. This second number gets killed off by 2 in front, the first number, so it's somewhere in there that gets killed off. The second number here gets killed off by something 2 in front, the first number in a parentheses, 2 parentheses away, so something in there kills off that one. So the only thing left at the end of all of this, okay, this is where we get the collapsing from. Everything pretty much on the inside here cancels out, and the only thing left for S sub n is a 1 plus a half, which is 3 halves, plus over here a negative 1 over n, and then another 1 plus a negative 1 over n plus 1. That's S sub n. And now what we do is we take the limit as n goes to infinity of this, 3 over 2 plus negative 1 over n plus negative 1 over n plus 1. And that is what? That goes to 0, that goes to 0, so I just get 3 halves. So this telescopic or collapsing series converges to 3 halves. Okay, that was number 25. Let's look at 26. Natural log of n over n plus 1. Natural log of n over n plus 1. Sum 1 to infinity. Natural log of n over n plus 1. Now they tell you again that this is a collapsing series, but let's act like we didn't know that. So I would probably start this with the nth term test. I would take the limit as n goes to infinity of natural log of n over n plus 1. The inside is infinity over infinity, and when you do L'Hopital on that, you're going to show that goes to 1. Natural log of 1 is 0, so this thing goes to 0, which means this test fails, right? So then you look at that, and I don't know, maybe you try starting to plug some numbers in. If you let n be 1, you get natural log of 1/2, plus now you let n be 2, natural log of 2/3, plus natural log of 3/4, and there's really nothing canceling out, it's all addition. So in order for it to collapse, we have to turn it into subtraction. So what we notice is that we can use the property of logs and split this into 2 logs, right? So if we have division inside of a log, it can turn into subtraction between 2 logs. And now when I write out the series, let's see what I get. If n is 1, I get natural log of 1 minus natural log of 2 plus natural log of 2 minus natural log of 3 plus natural log of 3 minus natural log of 4 plus, and then I keep going with this. And now I see some canceling. This is going to cancel with this is going to cancel with this is going to cancel with the next one, and so on and so forth. So that's actually going to be a nice collapsing series. So to do it correct, once I've identified that it does collapse, I'm going to write out what S sub n is. So that means I'm going to write this sum out, but I'm going to stop, okay? So natural log of 1 minus natural log of 2 plus natural log of 2 minus natural log of 3 plus natural log of 3 minus natural log of 4 plus dot, dot, dot. And then let me stop at n. That'd be natural log of n minus natural log of n plus 1. That's what I get when I plug in n. The one before this would be natural log, let's see, I'm plugging in n minus 1. So natural log of n minus 1 plus natural log of n. So when I plug n minus 1 right here, I get n. N minus 1 right here, I get n minus 1. And then I could do another one in front, but this is enough for me to see the pattern of what happens. You've got the minus natural log of 2 canceling here, minus natural log of 3 canceling here, minus natural log of 4 does cancel with something there. This one gets canceled by the one in front. So look, the ones that are right next to each other are going away. So the one right in front of this would cancel. This one should cancel with this. This one doesn't have anything over here. There's nothing over here for it to cancel with, so it stays. Natural log of 1 has nothing to cancel it because there's nothing in front of it. So our nth partial sum is natural log of 1 minus natural log of n plus 1. And natural log of 1 is 0. So this is just negative natural log of n plus 1. And so what happens here? We now say, all right, we found out what S sub n is. That's it right there. Let's take the limit as n goes to infinity of that nth partial sum. And if you let n go to infinity, natural log of infinity becomes infinite. So this heads to negative infinity. And that means this diverges. It's got to go to a number to say it converges. All right, number 27. N equals 1 to infinity. Three over n times n plus 3. Ooh, this one's going to be nasty. Okay, so I'll save us some time. The nth term test is inconclusive. It's going to fail because when you take the limit of the inside, it goes to 0. If you write out the first few pieces, nothing's going to cancel. So you go through and you do your partial fractions. You do 3 over n times n plus 3 equals a over n plus b over n plus 3. And let me save us some time here. What is it, 1? Comes out to 1 and negative 1. So a is, when you do your partial fractions, a is going to be 1 and b is going to be negative 1. So this becomes, this new series becomes sum n equals 1 to infinity of 1 over n minus, I'll just put the minus here instead of a plus, b over n plus 3. And I know I'm going to get some collapsing to happen here. So right now I'm going to start out with the nth partial sum. All right, so when I do the nth partial sum, I'm going to start plugging in numbers right here. When I plug in 1, I get 1 minus, let's see, 1/4 plus, let's see, 1/2 minus 1/5 plus 1/3 minus 1/6 plus 1/4 minus 1/7 plus 1/5 minus 1/8 plus 1/6 minus 1/9 and 1/7 minus 1/10 plus, and I have to stop this, but see I'm out of room over here. But I needed that many to see this cancellation. See, the cancellation occurs, let's see, this 1 doesn't cancel anything. This -1/4 cancels way down here. So the the second number in the parentheses cancels with the first number in the parentheses, 1, 2, 3 parentheses down the series. So second numbers cancel with first, 3 down to the right. So the second number here, oh yeah, these are gone, should cancel with the first number 3 down. So if I go 1, 2, 3, first number, there it is. So you can see this one and this one cancel, right? This second number here should cancel downstream. So I'll keep doing that, but I need to write the end of this, and I was out of room. So I'm going to do it like this. I'm going to start here. The last piece of my nth partial sum will be that with n plugged in, which is just itself. The one right before it is what I get when I plug in n minus 1. This is what I get when I plug in n. So when I plug in n minus 1 right here, I get 1 over n minus 1 plus 1 over n plus 2. So plug n minus 1 right there. N minus 1 plus 3 is n minus 2, or plus 2. The one in front of this is 1 over n minus 2 plus 1 over n plus 1. I'm going to do one more in front of that. 1 over n minus 3 plus 1 over n. And then in front of it, dot, 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 is this right here. So now getting back to this cancellation. We said the second one cancels with the first one 3 down. So that second one, this second one should cancel with the first one 3 down. 1, 2, 3, there it is. Gone, gone. This second one should cancel with the first one 2, 3 down. It does. So this second one should also cancel with something down here. All right? This second one should cancel with something down here. It does. This second one should cancel with something in here. It does. It's gone. Now, reverse that. Okay? Reverse this so that when we come from the other end, we do it the opposite way. Second ones cancel with first ones 3 down. That means first ones cancel with second ones 3 ahead. So first ones, here this first one, should cancel with something 3 down over here, which is in here somewhere. That should go away. First ones should cancel with something 3 down in here. It should go away. First ones should cancel with something 3 down. Should go away. This one you can see it. First ones should cancel with 3 down. Second ones, gone. So all the first ones are gone. Now how about the second ones? In order for the second ones to cancel, right, just like this one, we need to be able to look 3 down this way. So this one, can we look 3 down? Nope, can't do that, so it stays. This one, we can't look 3 down, we have to stop, so here. And this one here stays also, because there's nothing down here. So our nth partial sum is everything that's left, and I'll kind of highlight that. It's this, it's this, it's this, it's this, it's this, it's this. Okay? These first ones needed something down here to cancel. There was nothing down there. So it's establishing a pattern. It's somewhat complicated, I guess, the first few times you do this. So now what I'm going to do is I'm going to take the limit of this nth partial sum, which is 1 plus 1/2 plus 1/3, and then all this other stuff down here, plus 1 over n plus 1, plus, well, you know what? Did I forget to put minuses in there? Oh, I forgot to get minuses. Jeez, Robert. These were all minuses. I don't know why I didn't notice that earlier. Oops. Okay, so minus this, minus 1 over n plus 2, minus 1 over n plus 3. So let n go to infinity here. These all go away, and you're left with 1 plus a half plus a third. That's a common denominator there of 6. 6 over 6 plus 3 over 6 plus 2 over 6, which is 9, 11 over 6. 11 sixths. 11 sixths is the sum of that telescopic or collapsing series. I'll let you try 28 on your own. It's going to be collapsing. See if you can do that. All right, now the last sort of concept here in this section, which is kind of cool, I think. I hope I talk about this in class that I have time. The fact that when you look at the real numbers, if you write down a fraction, any fraction, doesn't matter what it is, you can always represent that fraction. So a over b. And here I'm saying a and b are integers, or elements of the integers, so that's coming out of the set. Like -3, -2, -1, 0, 1, 2, 3. As long as these are integers, you take any two integers and you divide them, then you're going to create what's called a rational number. All rational numbers can be represented as decimals, so this can be always converted as a decimal. But let me tell you something about this decimal. It either repeats itself forever, so it has like something where there's a pattern in there where it keeps repeating, or it terminates completely. So it's either like 1/4, which is 0.25, and then we say it terminates because there's really just 0, 0, 0, 0, 0. So we just say it terminates. Or if it goes forever, there's a pattern. 1/3 has the pattern 0.3333, so it repeats. Every fraction in the world is going to do either this or this. The numbers that do not do that are things like pi, and those will continue forever and never have a pattern. So if every fraction can be written as either a terminating or repeating decimal, then every repeating decimal or every terminating decimal should be able to be written as a fraction. And so that's what I'm about to do. I'm going to give us a repeating decimal, and we are going to have to write it as a fraction. And we'll use geometric series to do this. So we'll start out kind of easy, number 31. We're going to take 0.8888888 forever and write this as a fraction. So how do we write this as a fraction? Well, first thing I'm going to do is just write down what this is. This is equal to 0.8 plus 0.08 plus 0.008 plus 0.0008, and then forever, right? Because if I add these two together, I get 0.88. If I add them to this, 0.888, to this, 0.88888, and we keep doing that forever, we'll get all the 8s forever. Now this is equal to 8/10 plus 8/100 plus 8/1000 plus 8/10,000 forever. But this is equal to 8 over 10 to the first power, 8 over 10 squared, 8 over 10 cubed, 8 over 10 to the fourth, and so on and so forth, which is equal to the sum as n equals 1 to infinity of 8 over 10 to the n. And this is a geometric series. What I'll do is I'll rewrite this. Since the 8 does not have the power on it, I'll put 8 out here, and then I'll put 1/10 to the n. And hopefully you agree that 1/10 to the n would just be a 10 to the n on the bottom. And so all I need to do to make this geometric is to rewrite this with an n minus 1 up here, since this is an n equals 1 to start. So what I'll do is I will find my hidden 0 in there. So we've got sum n equals 1 to infinity. We've got the 8 out here. We've got 1/10 to the n minus 1 times 1/10 to the first power. Now this is just a number, 1/10 times 8. So that's just 8/10, 8 over 10, which is 4/5. And then 1/10 to the n minus 1. And that is the perfect format that we need for geometric series. This is this is r, this is a. The absolute value of r is less than 1, so this should converge. It'll converge to a over 1 minus r, which is 4/5 over 9/10, which is 4/5 times 10/9, which is, let's see, that's a 2 there, so that's 8/9. If you take the number 8 and divide it by 9 on your calculator, you should get 0.88888 forever. That's the first example. It's pretty clean. Let me do 33, and that will probably help you do number 32 and 34 on your own. So number 33, if you have 2.516 repeated, so the bar there means that the 516 repeats. So this is really like 2.516, 516, 516. See, the 516 is the part that continues. And we need to figure out what that means. Well, how about this? Isn't this 2 plus 0.516 plus 0.000516 plus 0.000000516 plus keep going. So I get the first 516 here, then zeros there, 516. So if I put those two together, I'll get 0.516516. And then when I put it together with this, I'll get 0.516516, and then I keep doing that. The 2 out here is not really following the pattern. So I just peel it off, right? That's 2 plus this decimal. So I have 2 plus, now let me write these as fractions. Remember the place value, tenths, hundredths, thousandths. So 516 over 1,000 plus tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions. So 516 over 1,000,000. And then 516 over 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. So what do we got there? 1 billion, and we keep going. Now this is just 2 plus 516 over 10 to the third. Hey man, come on in. And then I'm finishing up. This is the last problem actually, so I'll be done here in just a second. This is the 8.2 homework for my face-to-face class, but if you do this, look at this, you'll be able to do the one online. Plus, let's see, 516 over 10 to the 6th, and then 516 10 to the 9th. Okay. The pattern keeps repeating itself out here. So this is equal to 2 plus sum. So I'm going to rewrite from here down as a summation. The 516 is always on top. And I have 10 to the, oh man, what are these? 3, 6, 9, the next one will be 12. These are multiples of 3, starting at 3. So I would put 3n here, n equals 1 to infinity. It's kind of small. 10 to the 3n. So let's check it. If I plug in 1, I get 3 here, so 10 to the third, 516 over 10 to the third. If I plug in 2, I get 6, 10 to the sixth, 516 on top. And it should work. Now that's a geometric series. The 2 is still out front. Okay, and then what do we want to do? Let's take the 516 here times, let's look at this as 1 over 10 to the 3n. So 1 to the 3n is still 1, 10 to the 3n is 10 to the 3n on the bottom. Now remember, I need to make this for geometric. If I'm going to start my index at 1, I need to make that an n minus 1. I don't like the 3 being there. So I'm going to write it this way. 516 times 1/10 cubed to the n. And that way I can get this from this. Now 1/10 cubed is 1/1000th. To the n. And all I need now is to make this an n minus 1. So I'm going to make it a minus 1, but then remember I have to multiply by 1 over 1,000 to the first power. So I kind of did that really quick. And I should be able to get this from this right here. I have, let's see, 516 over 1,000 is my A. I'll put it right here. 516 over 1,000 is my A. I have 1 over 1,000 to the n minus 1. So this is my R, this is my A. And so I should be able to use the formula for a convergent geometric series. So we've got here, notice the 2 has just been coming along for the ride here. A is 516 over 1,000 over 1 minus 1 over 1,000. So 1 minus R, which is 2 plus 516 over 1,000 over, what's this, 999 over 1,000. And then I flip. So when I flip this, 1,000 here, 999, that's gone now. Thousands cancel, and I get 2 plus, let's see, 516 over 999. And finally, I need to put those two together. So I need a common denominator. So I multiply 2 times 999 on top, and on the bottom I have a 999. So 2 times 1,000 would be 2,000, but this is going to be 2 less, so it's going to be 1,998 over 999 plus 516 over 999. And I'm going to add those numerators up. So this is going to be 2,514 over 999. Yeah. Doesn't seem right. Hold on. I might have messed something up here. 2,514 divided by 999. No, I think that's it. What is this, 33? Oh, that reduces. It reduces, but this is fine. 3 goes in all of those. That's it. So that fraction, if you type it in your calculator, you should get 2.516516516516. Now I'm not going to do number 34, but I'm going to set it up because it's tricky. 34, they give you 10.135, but the 3.5 is the repeating part. So this is like 10.1353535. Okay, so the bar is only on the 3.5. So what I'll do is I'll rewrite this as 10 plus 0.1 plus 0.035 plus 0.00035. So notice that if I put these two together, I get 0.135. If I take that and add this, the first three decimals don't change, but then I have a 3.5 out there. I keep doing this. Plus 0.000035. And now I'm not going to touch these two. I'm only going to be looking at the part that's repeating. This is 10 plus a tenth. Common denominator there, 100 plus 1 over 10. That's 101 over 10. So that's this part. That'll carry with us the rest of the way. This part, you have to be careful. This is 35 over 10^100 thousandths, plus this is 35 over 10^100 thousandths, 10 thousandths, 100 thousandths. Did I get that right? Okay. And then the next one, 35 over 10, 1, 2, 3, 4, 5, 6, 7. So what you get here is 10 to the third on the bottom, 10 to the fifth, 10 to the seventh. And so when you do this, your formula is going to be a little different than the last one. Okay, you just have to create 3, 5, 7. You have to create the odd numbers starting with 3. So that's the important thing. You have to start with 3. So let's see how you do with that. It's kind of a challenging one. I'll tell you that the answer to that one should be 5,017 over, oh, well, you know what? Let me write it the way, not reduced. 10,034 over 990. And then you can reduce it. You can divide everything, reduce that out. Let me just double check it. 10,034 divided by 990. Yeah. That's what you should get when you do all of this work. All right. That is it for that section.